question show time. Your questions, my answers, as always, wherever you are on the channel. If a question pops into your brain, just write it down. I'll gather them up and I'll answer them here. No guest answerer this week, but if you have a YouTube channel and you want to jump in and be a guest answerer and you do like astronomy, science explaining, things like that, reach out. Just drop me an email, frasercain@gmail.com. Let me know who you are and I'll check out your channel and give you some questions. You know, one of my goals with my channel is to feature and promote as many science communicators as I humanly can. So if you want to communicate science, I want to help you get your name out there. So drop me an email. All right, let's get into it. John Rubish. With so many stars being found to have planets orbiting them, do we know from the stars that have been studied how many stars don't have planets? Or is it more that proving that there are no planets is actually more difficult since a planet may be too small or its orbit too distant to detect? I'll show you what the state of this problem is. We don't know of all the planets that are in the solar system, right? Right now, astronomers are trying to find Planet 9, which they can detect the influence of its gravity, but they haven't been able to find it. And that's just because it's probably so far away and so dim that we don't have the telescopes to be able to find it yet. And the next generation will probably find it. I also heard a really cool proposal that TESS could actually find it. But anyway, maybe that's another video. So what that means is that we will never know how many planets there are in the solar system for sure, because the solar system is really big. It extends out a couple of light years from the sun. And then the same goes with other solar systems. All we can do is find planets in those solar systems. We can never confirm that there are no planets in them. You know, it's that idea that you can't prove a negative. So as the technology gets better, as the telescopes are able to directly image planets orbiting other stars, stars that we thought used to have no planets, we will discover that they do have planets. And over time, astronomers will get to this point where they've got what they think is a pretty good estimate of the number of planets around every star. But at the end of the day, better techniques, better technology, we're still finding moons around Saturn. And as the techniques get better, as the telescopes get better, the number of moons that Saturn has just keeps going up. So just get used to that. Thomas Doyle. With the proverb, necessity is the mother of invention in mind, do you think that if we found out there was some kind of catastrophic astronomical event that posed a threat to us 10, 20, 30 years from now, and our resources and finance would be obviously directed towards that concern, would that spark huge steps in technology, putting us years ahead of where we would be if we just happily complacent without such a threat? We've seen examples where humanity, under enormous threat, has had to pull together to sort of pull together towards some specific goal. And unfortunately, it's wars, right? In World War II, World War I, the nations of the world put as much of their economies into the manufacturing of weapons of war to kill each other with. And for a lot of these countries, it was a state of life or death. You know, these countries would be invaded and they would be subjugated. And so for them, they had to do as much as they could to defend themselves. And so I think we've seen how that can play out many times in human history. And it's humans doing it to other humans. So if there was I mean, humanity has never faced a single global threat that we have. I mean, maybe the ozone layer is sort of a good one example of that, where you've got this situation, the scientific consensus is in, it's very clear that the refrigerants that we're using are diminishing the ozone layer, and so around the world, people cut the use of these chlorofluorocarbons and the ozone layer starts to recover. And we're going to go through that again, obviously, with carbon emissions and climate change at a larger level as the world tries to come to grips with the amount of carbon that they're emitting and try to bring those levels down so that we can minimize the amount of climate change. So an asteroid inbound would be sort of the same kind of thing. But then there are lots of situations where we know there are big problems. Where I live on the west coast of Canada, we know that there are enormous earthquakes that can happen every few hundred years that will cause tsunami and wipe out coastal cities. And yet we live on them and we build on them. And so we know that's coming. We just don't know when. And so I think that's the key, right? Is that if you had this moment that you knew this event was going to happen at a specific time, then that would be enough of a motivation to sort of gather everyone in the world and try to prevent this threat. But I can sort of see different versions have played out. But this very specific one of an asteroid strike coming our way, 30 years to prepare, that's never happened before. And so I'm not sure how organized we'll end up being to try and prevent something like that. Craig Corson. Regarding the second question about searching for ET, there is no alien civilization anywhere that will ever be a threat to humanity. It makes no economic sense to come here and take what we have, regardless of how their economy is structured. I'm really enjoying having this long, protracted argument over this debate over the Fermi paradox with the viewers. This is a lot of fun. Keep them coming. So this idea that there is no economic incentive, there's no reason to cross the gulfs from world to world, from star system to star system, to invade another civilization and take their water or metals or whatever, their technology or culture or who knows, right? The Borg, you'll be assimilated. So I agree that none of those really make a lot of sense. It's a lot easier to harvest the resources of your local star system than to try and cross the Gulf. And then if you could like find the water, then to bring that water back to your original star, it's crazy. No one would do that. But the reason a civilization would send out probes and interact in a hostile way is to prevent a future competitor. So we here on Earth, as we watch Starship launch and we become a spacefaring civilization, and eventually we will develop the technology to attempt to reach other star systems, and we will want to know at least who's out there, right? We're going to want to send self-replicating robot probes to other star systems to just see what's there and find out if there's any dangers. Is there a galaxy-wide civilization that could wipe us out if they wanted to? And so you can imagine a very advanced civilization saying, okay, we live in the Milky Way, we know that there could be other civilizations out there, and in the future, they could be a threat to us. Therefore, we are going to wipe them out. We're going to attack first. We're going to find out, as they reach these levels, and we're going to make sure that they don't pose a future threat to us. And there's been some really great books. I mean, there's the three-body problem. There's the Berserker probe concept. So there's been a lot of really great thinking on this matter. And that is unfortunately, that is sort of the most compelling reason why an alien civilization would explore the Milky Way, is to prevent future threats. Scott Collins. Wait, I can just be one of your biggest Patreon supporters and have my name be whatever I want and you have to read it? For example, the late Zorgar the Immortal, the Undying, Child of the Gods, Creator of Time, Ruler of all that is or will be eternally, may he rest in peace? Yeah, I mean, I'd probably want to shorten it, especially if we want to try and put it on the screen and have it fit within all the other names. So, maybe we'd call you, what's your name again? Zorgar. We'd call you Zorgar the Immortal, maybe. That'd be room for that. But if you want to stick to being a pseudonym and be one of our biggest Patreon supporters, I'm down with that. Dustin Moore. Why don't they just connect the photon laser about 20 feet behind the sail on a pole so that it's constantly hitting it full force? This is related to the idea of a solar sail and, the breakthrough star shot that you use a powerful laser to send these tiny nanoprobes from star to star using a laser. And the laser fires and it impacts the sail and then the sail heads off. And so your idea is to put the laser on the sail, and that way the laser is always just shooting at the sail, and that way it keeps the propulsion system. So the problem with that is the same reason why you can't just put a big fan on top of a sailboat and then have the fan push the sail. Although I know like Mythbusters did that, it kind of worked, but in the vacuum of space, this won't work. And that's because the laser, as it fires, as the photons are leaving the laser is actually getting a kick in the opposite direction. And this is called a photonic engine. And so it's proposed as a kind of space engine that you could do where you shoot out a laser, and just the force of the photons, the momentum of the photons leaving your laser will give you a kick in the opposite direction. And so in this case, if you had a big powerful laser on your spaceship and you fired at your solar sail, the laser is going to be pushing you this way and the solar sail is going to be pushing you that way, and you're not going to go anywhere. Pyronac 1. Everyone says nothing is faster than light, but I've heard that neutrinos go faster than light in a pure water source. Is this true? If you ever hear when people say that nothing can go faster than light, they usually add nothing can go faster than light in a vacuum. And that's because in the vacuum of space, that is where light can go its maximum speed. But when light is going through some other thing like water or air or fiber optic cables or jello or rubidium crystals, the speed can change dramatically. And so while neutrinos are going close to the speed of light, but they don't care really about whatever it is they're going through. They'll go through the Earth, they'll go through a light year of lead, they'll go the same speed. And so you can imagine you fire a bunch of neutrinos through water, and the neutrinos are going at pretty much the speed of light, almost, while the light slows down as it goes through the water. And so the neutrinos go faster. And so always, it's about light speed in a vacuum. And that's the 300,000 kilometers per second. Michael Bear. How would you calculate Hubble's exposure time for outer planets or stars or galaxies? All right, so this was based on last question show where people wanted to know, like, what is the shortest exposure time? So whenever you do astrophotography, the key is, well, on Earth, when you've got your telescope sitting on Earth, and you're doing astrophotography, you've really got sort of two things that you're trying to work around. The first thing is that you don't want to overexpose your image. So, if you take a picture of the moon, but you take a 3-minute exposure of the moon, all you're going to get is just this big white spot burned into the middle of your photograph. So you need to take a much shorter exposure of the moon, like 1/60th of a second. And that's when you start to see the features, the craters, the things like that. And so if you wanted to take like a really nice high resolution image of the moon, you would take thousands and thousands of images 1/60th of a second, and then you would stack all of those images together to make a really beautiful picture of the moon that was sort of the combined data of all of those ones. And then the other thing that you're trying to minimize is essentially the movement of the Earth, the blurring of the atmosphere, things like that. So for example, if you set up your camera and you take a picture of the Milky Way with your camera, if you leave the exposure for longer than, say, 25, 30 seconds, it depends on your lens, you're going to get all the stars are going to start to make little trails. And so you can't make an exposure longer than about, say, 20 or 30 seconds, and then otherwise you'll get star trailing in your image. So with Hubble Space Telescope, it can point and track really well at whatever target it's looking to go after. But then it has that same problem with the moon. It's a really, really powerful telescope. And so you open it up, you point it at, say, the center of the Orion Nebula, and it's going to become this overexposed mess in just within a couple of minutes at the most. And so what astronomers will do is they'll figure out what is the longest exposure they can take so that they don't get any part of it overexposed, or the parts they're looking for. And then they'll take a whole bunch of exposures at that same length. So it might be that if you're taking a picture of like a really faint nebula, maybe you can do a 5-minute exposure, a 10-minute exposure, a 2-hour exposure, or maybe it's only a 30-second exposure. Each object is its own special creature. And then they take as many images as they have time for. So maybe they might have a day on the Hubble Space Telescope or a week on the Hubble Space Telescope. So let's take picture after picture after picture after picture, and then they will use software to stack up all of those pictures. And essentially what it's doing is it's looking at every single picture and going, is this pixel noise, like just some kind of cosmic ray or an asteroid moving through the screen, or just some change in temperature on the CCD, or is it data? Is there actually a little bit of light there, and what color is it, and what wavelength, and so on? And if you take more and more pictures over time, you will get a much better, more data-filled picture. And the longer you go, the better these pictures take. And I'm going to show you an image that was taken by Dustin Gibson, who works at Oceanside Photo and Telescope. I think this is a 90-hour exposure of a nebula. And the key with this is he didn't do one 90-hour exposure. It would have completely gotten overexposed. So instead, he took tons of smaller images, as long as he could, probably in the sort of 5-minute range, and then he stacked them all up, and he got all that really amazing faint data. And that's the advantage of doing longer exposures and stacking them all up. Loban. The collapsing question may have meant to spiral in and collide, maybe? If that was it, what would happen if two main sequence stars spiraled in and collided in their planets? That could be the question. Yeah, so this was based on the question last week about like what would cause stars to collapse on themselves, and I sort of had interpreted as the stars just kind of, collapsing like supernova, but a couple of other people in the comments said, well, maybe they're, what the question meant was like they're spiraling inward and they collide with each other. And so there are a couple of ways. Like normally with two stars, you got two stars going around each other, and they're just going to go around each other for billions and billions of years. There's no forces acting to slow them down, to cause them to spiral inward. But there are gravitational waves. So as these stars are moving around, they are releasing energy as gravitational waves. And that energy actually is taken away from their orbital momentum. And so over very, incredibly long periods of time, and it all depends on how far away they will spiral into each other and eventually collide. And you can see this with things like pulsars and even like the collisions between black holes. A lot of the times they've been orbiting each other for hundreds of millions of years, and it's only finally in the very end they will collide. And they're essentially emanating gravitational waves, and that is causing them to lose their orbital velocity, and they're coming in together. And then the other way is if there's some kind of stuff in the area, some kind of gas or dust, something that causes friction on these stars as they're moving around. And what you'll get, which is really amazing, is you get this thing called contact binaries. So you've got two stars, they get closer and closer and closer, and eventually they cross the Roche limits of each other, and these blobs of material will sort of extend out, and you'll get this sort of like a dumbbell orbiting around itself, and then eventually the stars will merge, and it causes a bad day. Now, I talked to an astrophysicist about this a bit, and sort of like, when would it be a bad day? And his opinion was that it would be a bad day for a long period of time. If you got to the point where these two stars were starting to merge and they were, they passed within the Roche limit, they're already moving their way towards a contact binary, then there would be tons of radiation and all kinds of stuff in the environment. And so for anyone living on the planets nearby, it would be a bad day. And eventually it would merge, and it depends on the mass of the stars. They might turn into one new star. They might sort of turn into one of these ideas called a blue straggler. So where they might be very old stars, but now suddenly they look like new stars because there's all this fresh hydrogen mixed up and they are bigger and hotter. Or they might just collapse and cause a supernova. So it all just sort of depends on what the stars were. But I hope that now we've covered every version of that question. Mark Grant, why don't they land tracking devices on asteroids suspected of being a threat to Earth? That is a great question, and actually this is one of the plans. So there's a company called the B612 Foundation, and it's led by a bunch of astronauts, and they are quite concerned about the danger of asteroids in the future. And so one of their ideas is to build a space telescope called the Sentinel. And the Sentinel will help search for asteroids that are potentially dangerous. And they have also proposed that one of the best things that we can do is send some kind of tracking device to an asteroid, land on the asteroid, clamp onto it, and then that will serve as a beacon that then will allow astronomers to track the position of that asteroid as it moves with great accuracy. The movement of asteroids is actually more complex than we ever knew. They've got interactions with other asteroids and bodies, Jupiter and the gravity of the Earth and things like that. But there's also, say, the sunlight that's coming from the sun that causes the asteroids to rotate in funny ways that, the solar wind is pushing on them, kind of like a solar sail. And so over time, the movements of these asteroids, they're more complex than they know how to predict. And so this is their idea. And I think it's a great idea. And I hope that it actually happens as the next set of space missions go forward. But definitely go and check out the B612 Foundation, and you can get involved. They take donations. They do a lot of outreach about asteroid safety and dangers. And I think, you'd find it really interesting. Micro Chandran. Hi Fraser, do all neutron stars start off as magnetars initially, become pulsars, and then quiet down to just be neutron stars that do not spin? Magnetars have been a bit of a mystery for quite a while. They are neutron stars, like pulsars, like regular neutron stars, but they have this just incredibly high magnetic field that is around them. And astronomers wonder, what could it take to actually create a magnetic field that's strong? It will tear your atoms apart at an atomic level. The magnetic field is so strong. Of course, if you got that close, you'd be bathed in radiation and the gravity forces would be pulling you apart, but also the magnetism would be tearing you apart at a molecular bond level. So that would also be painful. So how do they form? And actually, just like in the last week, there's an interesting new piece of research that says that actually what it looks like is you've got two stars. They do that thing that I mentioned earlier in the episode. They're orbiting around each other in some binary system. They come together and they form a new star. And it's that process of these stars coming together that kind of whips up this new star to give it this incredibly powerful, really weird magnetic field. And then the thing explodes as a supernova, and you're left with a neutron star as the remnant, but it still has this incredible, powerful, complex magnetic field. So it looks like the thing that distinguishes regular neutron stars from magnetars is this process of stars merging first, then detonating as a supernova, as opposed to just one star detonating as a supernova. But, you know, it's an interesting step, and I should do a video about that. Simon West. You mentioned that we can't destroy the Earth with our carbon emissions and turn it into Venus. This has been bothering me a lot. I hope we don't wipe ourselves out, but the planet is the important thing. Intelligent life could come back. So is there another way we could destroy the planet in a literal sense? All the nuclear bombs going off at once? There aren't a lot of ways that we can wipe out humanity forever, and even less ways that we could wipe out planet Earth. If we wanted to wipe out humanity forever, right, we could try exploding all the nuclear bombs. We could try putting ourselves into a climate change disaster that we weren't able to adapt to. Global pandemic, right? Any of those would wipe out humanity, but not sort of over the long term, the planet would recover and then it would never know that we were here. But there's a couple of things that we could do, right? Imagine if we develop artificial intelligence and it is really smart and we tell it to make paper clips, you know, the classic paperclip optimizer, and so it dismantles planet Earth into paper clips. That would be bad. That would be bad for the planet forever and possibly the entire Milky Way as the paperclip optimizers head off into the Milky Way to turn every planet and star into paperclips. And then also there's been this idea that there are some science experiments that could cause some kind of cascade. So we could turn on the Large Hadron Collider, we could create a black hole that could drop into the Earth and it could scoop up the inside of the Earth and collapse it from within, or we could turn the entire planet into some exotic form of matter like strange matter or something like that, and then that would propagate out into the universe at the speed of light, and then we would have destroyed the whole universe. So there's no easy ways to do this, but I'm sure as our power and our capability grows, we will start to develop the ability to not only wipe ourselves out, not only wipe current species out, but actually maybe wipe out the Earth and eventually maybe wipe out the universe. But I don't know of any practical solutions to do this right now, so I wouldn't be that worried about it. Brush your teeth, exercise, eat healthy food. That's what we need to be worried about. Martin Wilk. Can a brown dwarf still become a star? A brown dwarf is a kind of star. A brown dwarf is really a star that has less mass, and so it doesn't have enough pressure and temperature at the center of the star for it to be able to fuse hydrogen into helium. You need to be a red dwarf star, and I think the least massive possible is about 15% the mass of the sun. And so if you have less than 15% of the mass of the sun, you'll get a brown dwarf. And the thing that really differentiates a brown dwarf is that it still has enough temperature and pressure in its core to be able to fuse a version of hydrogen called deuterium. And so it can still generate heat through a kind of fusion, and then it runs out of fuel in its core, and then it just goes quiet and, you know, cools back down to the background temperature of the universe. And so could you turn a brown dwarf into a star? You would have to add mass to it. So if you smashed a couple of brown dwarfs together and you could get above that 15%, then you would be able to initiate fusion in the core of the star, and then you could go. And if you wanted to do that to Jupiter, you could crash another, say, 77 Jupiters into Jupiter, and then you would have enough temperature and pressure, enough hydrogen there to be able to create a new star. So really, if you can just get more brown dwarfs, smash them together, then you'll be able to make a star. All right, great questions this week. Thanks, everybody. As always, wherever you are, question pops in your brain, write it down. I'll gather them up. I'll answer them here. All right, I'll see you next week.